Hello students and welcome to the video lecture on chemical reaction engineering. We are continuing our discussion on catalysis and catalytic reactors. As a part of this unit, we have been discussing on the different reactor systems that can handle the deactivating or decaying catalyst. Prior to this, we have already discussed on the different types of deactivation, the different rate laws of decay, how they are being concerned with the concentration of species and the decay in the activity of catalyst. We have also discussed one of a system which can handle the decaying catalyst when there is a very slow decay, one being temperature time trajectories. We have developed an expression which talks on how a temperature has to be increased for a reactor with time so that the rate of reaction remains constant from the initial temperature to the elevated temperature, so as that the decay of a catalyst does not hamper to the conversion or throughput from the process. And this was the case when the decay law was very slow, was slow decay. Now today we are going to talk on moving bed reactor where there is a moderate decay of a catalyst. So we start with moving bed reactor. So you can have a look at the schematic here. We have a reactor on the left. So reactor is being fed from the top. You have a catalyst which is coming through the separator, also fed from the top. Feed and the catalyst moves through the bed in a downflow. The products are removed from the bottom of reactor. The catalyst moves into the kiln or the regenerator. Now this is the temperature zone where the catalyst is being regenerated, but the gas which is coming through feed is not sufficient to elevate this. So you have a secondary air which is coming through the bottom, which lifts up this complete catalyst to the separator. Density difference causes it to separate. Catalyst will get settled in the separator at the bottom and the lifting air will go out. Again this catalyst will move down in a back bed into the reactor. And this is how this is where the reactor, air's regenerator, and then there is a separator combination. So this moving bed reactor. Let us have a brief into what we reaction system with the significant catalyst decay rate requires a very quick regeneration and the replacement of the catalyst, and that is where moving bed reactor will help. The catalyst which is deactivated will move to the regenerator, get clean up and goes back to the reactor again. Now there are two types of reactor which usually handles the faster decay. As we have said, when it is moderate decay we go for moving bed reactor, and when it is a very fast decay we go for straight through transport reactor. So we are going to discuss STTR in the later part of our next lecture. So why we are saying it to be a moving bed rather than a moving catalyst alone, what happens is the freshly regenerated catalyst enters to the top of the reactor and moves through the reactor as a compact bed. Point to be noted. The reactor as a compact bed. This multiple catalyst particle comes together and slowly moves as a compact bed through the reactor. That is where we have called this as to be moving bed reactor. Now, if the reaction is either poisoning or aging or segregation, this may not be applicable. This is applicable where regeneration is possible. If there has been a coking through the reactor, that is where it is possible to have usage of this reactor. So the catalyst is coked and moves through the reactor until it exits the reactor into the kiln where the carbon is burnt off. The regenerated catalyst is lifted. Point to be noted here. Catalyst pellets are typically of 1/8 to 1/4 inch in diameter. If you want to put it in mm, 25 mm is 1 inch, so roughly 5 to 10 mm. Roughly it is 3 to 6 mm. That is what we are talking of as the particle size. Now the reactant feed stream enters to the drop and flows backward. So let us have a mole balance onto the reactor. What we are trying to do here is, let's say from Z to Z plus del Z, it is moving. The rate of catalyst somewhere W to W plus del W. US is the mass velocity of the catalyst. Here I will denote as the flow of reactant. So we say mole balance of reactant over the rate of the catalyst. So you have rate of flow of A in, rate of flow of A out, plus rate of reaction or generation, that is equal to accumulation. There is no accumulation, so 0. If I rearrange this becomes dF by dW is equal to minus RA. Now FA is FA naught into 1 minus XA. If we derivate this, that becomes FA naught into dx by dW equals to minus RA. Now my RA is function of activity, rate constant, and the initial rate, which we can say K into function of concentration of species. That is what this usual rate is. So let us keep this equation with us. F naught dx by dw is minus RA. Now there is another rate which we should be concerned, that is the rate of decay. So the decay rate is dA by dt, kd a raised to power n. So n can be either 1 or 2, as we know that. But let us have a quick look. This conversion is with respect to rate and deactivation is with respect to time. That is what we need to uniform. So we need to relate this contact time to the weight of catalyst, and that is where we will use mass velocity of a catalyst, that is mass per unit time where the solid catalyst is moving. So mass velocity, you can write it as W upon time, which can, on the other way around, we can write the time that the catalyst has been in contact with the feed, T, is weight by mass velocity. Now if I differentiate this, I'll get a dt as dw by us. If I use this term with 110, I get dA by dw. US goes on the top, so it goes on the other way. kd by us a raised to power m. Now I have two rate laws which are pretty much sync. Fn of dx by dw is minus Ra, and dA by dw is kd by us a raised to power m. If I solve these two equations together, I'll be able to see how my conversion changes with respect to the weight of catalyst in a moving bed reactor, and I can also tell how my activity changes, this being function of mass velocity. These are the simple equations, two equations for a moving bed reactor that we'll be using. Let us try to go through the problem and try to understand the application of moving bed reactor. So the example says the catalytic cracking of a gas oil charge, where we are taking gas as A, to form C5 plus components, which typically cokes out and gives the dry gas, which is being carried out in a moving bed reactor at about 900 degrees Fahrenheit. So the reaction is gas oil to give C5 plus components, plus there is a dry gas and coke formation. We just try to lump everything together to put it as A gives products, and there is a coking into the reaction. So the pure hydrocarbons are known to crack according to the first order rate. This is a known knowledge. But how this complete reaction has been taken, that is where they are called lump cracking rate, is presented by the second order rate law. So your rate of reaction is given as minus Ra, which is second order with respect to the reactant. The catalyst deactivation is independent of gas concentration, and it follows the first order decay rate law. You are given Kd, you are given here value of K. Important, this is per gram of catalyst mole minutes, right? And a typical volumetric thing, you will have it liter per mole minute. So 0.72 reciprocal minutes, that's the first order decay rate law. The feed stream is then diluted with nitrogen. Volume changes can be neglected, so the gas phase reactions epsilon is 0. The reactor contains 22 kg of catalyst. The weight of catalyst is given to you. Moves through the reactor at a rate of 10 kg per minute. So weight per time. So this is mass velocity of a catalyst is given. It's feed at a rate of 30 moles per minute. So molar flow rate is given. Concentration Ca0 is also given. So you need to find out the conversion that can be achieved in this reactor. So let us go back to what we already know. Conversion with respect to the rate is known to us. If we solve this, we will be able to know the conversion with respect to the weight of catalyst. But this rate is function of activity, and that activity is solved using Kd by us a raised to power m. So we need to have solved two different rate equations, one being the rate expression and other being the decay law. So rate expression is Fa0 dx by dw is a into minus Ra dash, that is with respect to weight of catalyst. Your rate law is minus Ra is K into Ca square. This is our design equation, this is our rate equation. Our dk is minus dA by dt kdA, n value is 1 here. We know dA by dW is kd by US a raised to power n is 1 here. Now using this equation, now f is 0 dx by dW, a I can get from this expression. If I integrate this from activity 1 to a, I will be ending up at a equals exponential of minus kd by US into W. This a along with this rate law, if I put it in this expression, f is 0 dx by dW, you have a, that is exponential minus kd by US into W, and your rate law is k into ca square. Ca is ca naught 1 minus xa square 1 minus x whole square. Now if I separate the variable and integrate, I use second order rate law. On the left I should get x upon 1 minus x. The rest of the things from here moves on the other side. K ca naught square upon f naught. When I am integrating this exponential of kd by US into W, I'll get a similar expression from 0 to W, 0 being 1, and I'll get kd by US, so kd and US. So this becomes my final expression, which I can solve to get the conversion in this reactor. So you have k value known to us, Ca naught value available with us, mass velocity known to us, mass flow rate known to us, decay rate constant known to us, weight of catalyst known to us, again decay rate constants and mass velocity. So everything on the right side is known to us. Only unknown variable here is conversion, which we can be able to solve. Let us move ahead to see k value 0.6, Ca naught square 0.075. Now there has been the balancing of this rate of catalyst. So mass velocity is given, and if you solve everything together, you end up at 55% conversion. So it's a pretty simple example where we have to go through a design expression, solve for the rate law, decay law, use the decay law, feed it both the laws into the design equation to get conversion as the function of known variables to get the value of conversion. Now dam color number 2 for a second order reaction. What we have solved it is for this is what we have: second order rate law. We know second order decay. We know second order dam color number is kCa0 tau, right? Tau is V by V naught. But in case of for a second order reaction divided by 8 for a packed bed reactor, we have kC0 square W by Fn naught. That becomes kC0 W by V naught. This is a very specific dam color number for second order reaction. There is a dimensionless decay time that is given by lambda is kd into t. We know this is W by US. Using this decay dimensionless decay time and a dam color number, this expression has been given for a moving bed reactor. Conversion is dA2 1 minus to power minus lambda plus dA2. Now this has been specifically given by a different scientist, that is with solve directly through this expression. If you not go through all of those, and if you use directly this formula, you'll still be able to get the value of conversion here. So that is what we have for the moving bed reactor. Let us have a quick recap on what we have studied for the day. We have seen the schematic where catalyst bed moves through the reactor, gets regenerated into the kiln, moves to the separator through the secondary air, separates out the air and feeds back the catalyst. That is our moving bed reactor, which handles the moderate decay of catalyst, typically which is done by fouling or coking of catalyst surfaces. We have gone through the mole balance to get the design equation of F0 dx by dw is minus RA. RA is function of activity, which can be then be a function of which can be then taken from the decay or the deactivation law. We can solve both of this. So equation dx by dw is equal to minus RA, and this equation dA by dw is kdA of C raised to power. These two equations are the basic design equations that we should be using in solving moving bed reactors, and we have seen an example of catalytic cracking in a moving bed reactor where a gas oil is being cracked to get coke and products. We have found out the conversion using this design expressions. We have seen finally a expression given by Abid for the second order reaction, which uses the dimension rate and the second order Damkohler number. That is the end of a lecture for us. In the next lecture, we'll be discussing on straight through transport reactor, which will handle a very fast decay of catalyst. That's all for the lecture today. Thank you.